Let's start coding the derivative part of the video. I mean the backpropagation algorithm. We'll start with first writing some helper functions. So the first one we'll be needing is calculation of softmax. It will receive an input of torch dot tensor. We won't be needing any dimension for this particular thing because yeah, there is just a single vector, so we have to apply along that dimension only. So we won't be getting into anything into that. Like unlike the attention video, so it will be torch dot tensor, and then we can exp is basically torch dot exp x. So for each element it will do e raised power x, and then we can write this denom as uh, torch dot sum, and then torch dot sum of exp, and let's keep the dimension is equal to 0, so it will sum the entire column. And then we can just, for this we can do keep dimension is equal to true, and then we can simply return torch dot diff exp by denom. So yeah, this will get us working with the softmax value. The second function which we have to work with is calculation of derivative of tan h. So we have seen the tan h function, like we have to calculate the f prime. So tan h of x is basically e raised power beta x, like yeah, e raised power beta x minus e raised power minus beta x divided by e raised power beta x plus e raised power minus beta x. So ignore the beta for now. We'll adjust in after calculation of derivative. So we have to derive with respect to dx of, let's call it f. So differentiation of function f with respect to df. So it's basically u by v form. So its derivative will come out to be basically v du by dx minus u dv by dx divided by v square. So this is our u and this is our v. So let me just check if the tan h I have written is right or not. Minus and then plus, yeah, correct. So this is u and v. So du by dx, if you do du by dx, it will be what? It will be let's ignore the beta for now. Beta will unnecessarily cause complications. We'll adjust well after calculation. So du by dx is what? E raised power x plus e raised power minus x. dv by dx will turn out to be what? E raised power x minus e raised power minus x. And then when you multiply v with, when you calculate v into du by dx, so v is the same thing, so it will basically become a square. And similarly u, when you multiply u with dv by dx, again u is your e raised power x minus e raised power minus x, so it will come out to be square. So if you divide it, if you subtract it and if you divide it, so it will be basically e raised power x plus e raised power minus x का whole square minus e raised power x minus e raised power minus x का whole square divided by v is your e raised power x plus e raised power minus x का whole square. So if you just take it out one out of the term, so it will become separated out 1 minus e raised power x minus e raised power minus x by e raised power x plus e raised power minus x का whole square. So this will become 1, this will simply become 1 minus f square of x. So where f is equal to tan h for our case. Now if you can adjust the beta, so beta will be constant term, it will come out to be out, and then it will become beta x. Simple as that. So this is our derivative for the tan h, and let's see, it's pretty simple and we can code it right away. So def tan h derivative, what we will be needing x, which will be a torch dot tensor, and then we'll returning it torch dot tensor. Then we can simply return also we can take beta, let's take it 1.0, 1,0, beta torch dot float type. By default we'll assign its value to be 1.0, and then what we can do, return beta into 1 minus 1 minus, sorry, not I, 1 minus, we have tan h function defined over here. We have tan h of the same x, and then we can raise its value to be 2, and then we can provide it beta. Uh, Pretty simple, pretty neat. We are done with tan as derivative, and then what another thing we'll be needing is this is pretty much it for the derivative section, I guess. Okay, torch is not defined, I haven't run this. Let's rerun all these things. Cool. Let's initialize this also. Forward pass we have done. We won't be doing this and this. So for the derivative point of view, we have to write, so we had to calculate two derivatives, one which we had already written. So this basically we should place it over here. Tan s derivative is done, and then we have to derive the loss with respect to z. We're not when we derive the loss with respect to z, it basically comes to be s minus y. S is the softmax probability, and then y is basically your actual label. So yeah, let's get def derive derive loss, or let's simply loss with z. Loss with z will be needing let's calculate z, which will be torch dot tensor. We'll be needing an actual value, which will be again be a torch dot tensor, and then we'll return torch dot tensor. Simple. So first we have to calculate softmax probab, which will be basically softmax of z. Let's not keep dimension. Dimension by default, I think it is 0. It should be 0 only. Yeah, dimension is equal to 0. So we got the softmax probability, and then what it's basically doing is s minus y. So softmax we are having, we have an actual value. We can simply return softmax probability minus actual value. So I think this is done with the loss of z. Now we'll be going towards the computation of those particular derivatives. Now let's define a backprop function. So for the backpropagation function, what all things we'll be needing? We'll be doing a forward pass. So for backpropagation, we'll be updating the weights. I assume no, we won't be updating the weights. We'll be just for this particular backpropagation function, we'll be simply returning the derivatives whatever we are getting. We won't be updating anything. So yeah, let's start. Let's get the value of activation. Activation will be let's not make it torch or tensor, let's make it a list, and then you'll be getting some z value, which will be again be a list. Yeah, so we are having two activation values, a1 a2. Let's make it activation, and then we have three z values, z1 z2 z3. Let's make it of z. Now we have to make it a bit of more modular code. So what we can do, let's first create this with d of z3. D of z3, what will be, you have to calculate this loss with z, and then you can pass it over here z3, and then okay, so I'll be needing the actual tensor also, actual, which will be our torch dot tensor z3, and then actual. So it will give me s minus y thing, right? Now d of z3 is calculated. D of z2, if you do, so d of z2 is simply basically what we have done, d of z2 for d of z2. Yeah, so for d of z2 we have this particular thing. This is d of z3. We can multiply w3, and then we can take the f prime, and then we can multiply the a1. So we have to multiply these things. So we can do torch dot matmul. Now we need the weights also, so let's add this. IGSTS weights will be list. Let's take it out. We are not doing on biases because yeah, it will work fine for the same thing also, but yeah. Now what we have to do, we have to multiply d of z3 with w, right? D of g3 with w, and then we have to calculate the derivative of z2, and then we have to multiply a1. So let's do this. W3 comma d of z3, then into this is element wise multiplication basically. So z3 with this is done, and then we have to multiply derivative of tan h into tan h derivative, and then we have to pass over here z2. Cool. So we are done with these things, and then let's do simply just like this. We can do d of z1. Just copy this, paste it over here. Instead of w3 it will be w2, d of z3 it will be d of z2, and z2 instead it will be d of z1. I mean z1. Okay. Cool. Now we have to calculate with respect to weights. Like for each of the g value we have calculated, now we have to calculate with respect to weights what we are getting the particular derivatives. So for the weight multiplication, we have to simply multiply the activation functions with these three values. So we'll be getting the same thing. So let's calculate d of w3. D of w3 will be simply we have to multiply torch dot matmul. For w3 we have to multiply activation with d of z3. But to maintain the shape and all, we have to take a transpose also. Torch transpose d of z3 comma 1 comma 0. So you will get d of w3. Simply you will get d of w2. Just copy, paste, and then a1. Instead of z3 you will having z2, and then simply you will getting d of w1. For when you will come to the last layer, your z activation values have been exhausted, and then you have to take the inputs also. So you will needing the input vals dot pencil. Simple thing, just copy, paste. Instead of a1 it will be input vals, and instead of z2 it will be z1. So that's pretty much it. So you have calculated all the derivatives of the weights, and then now I can simply return d of w3, d of w. Let's do like this: w1, w2, and that's the toughest code whatever is there in the backpropagation. Like we have written it, and pretty much it's done. Now all we have to do is like we have to write the training loop, and then we have to keep iteration, and then we have to keep updating the weights. So we have this particular data. Yeah, one more thing which let's start by reading the data. Or do we have the data read? Okay, let's we already went through the data, so just for the simplicity let's delete all this. We have the train data, we have the derivatives, we have the backpropagation. Let's start yeah. So from the train data, if we see train data dot head, we have all this. Do we have the labels? Did we drop the labels or what? I think we dropped the labels. Yeah, train data we are having this. Let's take out the actual value. Actual value will be train data label, and then we can do something like let's make it train data. Train data dot drop columns is equal to label. Now if we see train data dot head, yeah, cool. And then so we have our actual value, we have our train data, we have the forward propagation code ready, and now we can proceed it. Now, but before proceeding, we are having actual values as a single integer. We have to convert them into one hot encoding. Because yeah, that's how the cross entropy loss function will work over there. So let's convert it into one hot encoding. First, before converting into one hot encoding, let's see what's the shape of actual dot shape. What? Oh, sorry. We have already dropped it, so it won't be reading again. So just do this. Let's do actual dot shape. So it is approximately 60,000 comma. So let's just it's not good thing to do this will actual dot reshape actual dot shape comma actual dot shape at 0, 1. Series object has no attribute reshape. So what it can do is series object has no attribute. Why? Okay, so it's coming out to be series. Okay, we can convert into torch dot tensor. Can I convert it into actual? Okay, cool. Now I can then reshape it to actual dot shape at 0, 1. Let's see now actual dot shape. Okay, cool. Now it's coming 60,000, 1. This we did because while like in the previous video we mentioned that when we are summing it, if we are not providing it the correct dimensions, so it will, instead of adding those values, it will keep on stacking on the right hand side of the tensor. So that's why we need the actual to be having a shape of 60,000, 1 in a proper shape. Okay, cool. Now we are having the actual values. Now we can do hot encoding. On hot encoding, actual encoding. So for that we need to import dots and dot functional as f, I guess. Yep. And then we have to do f dot functional dot and then dot functional. I'm not sure which module as f. Yep, f dot 1. So now we have to do one hot encoding of the actual value. So what basically it does, it will take it out actual, and then if we see actual dot hot, so it is 60,000, 1, 10. We wanted 10, 1. So we just do it transpose 1, 0, 0, 1, 2, 1, I guess. Yeah. 2, 1, 2, 1, 0, 1, 2. Let me check once. 2, 1. Yep, it should give me correct. Yeah. So now we are having our labels in the correct format, whatever we required. Let's move to the next process. Next process is basically we have to do something for the train data as well. So now train data is we have dropped the label, and then train data we have to normalize the values. So each of the pixel is between 0 to 255. So what we can do, we can divide this entire train data, convert it into tensor, and then divide it with 255.0 to normalize the values. So what we can do, we can do something like let's float tensor train data dot values, and then we can divide it by 255.0. So that's done. And then if you see train data dot shape, yeah, so it's 60,000 comma 784. I think but what we have to do, like, it should be something like 60,000 comma 784 comma 1. Again, it's not in the correct format, so we can unsqueeze it, like we can add an extra dimension over here. Train data is equal to train data dot unsqueeze add dimension 2. The train data dot shape, it's coming out to be 784 comma 1. So we are having our training data ready. Now what we have to do, we have to initialize, and then we have to do the backward propagation. So I think initialization code we have already done over here. Okay, we haven't done. Okay, let's see. So your input 1 neurons will be how much? We decided to be 784. Input 1 neurons will be 784. And then what we have to do, we have to do input 2 neurons. Input 2 2 neurons will be equal to output 1 neurons, right? Let's just writing it for the sake of clarity. And then let's see, input 3 neurons will be simple output 2 neurons, and let's say they are 16. And then for the final layer, what we have to do, final will be final output number of classes, that is equal to 10. So these are our input neurons defined over here. And then what we can do next is, now we have to initialize the weights and the biases. So let's go with this. Weight 1 comma b1 is equal to initialize weight. So for the first, it will be size of input 1 neurons and then output 1 neurons. Simple. Yeah, 784 cross 64, 64 cross 16, and then 16 cross 10. So your will be input 1 neurons, and then output will be output 1 neurons. And similarly, w2 comma b2 will be, sorry, not d2, b2 will be initialize weight. It will be input 2 neurons and then output 2 neurons. So this is 64 cross 16. And then similarly, w3 comma b3 will be initialize weight. Okay, so it will be input 3 neurons, input 3 neurons, and then final output. So this is 16 cross 10. So this is our weights, biases, initialized. Now what we have to do, we have to write the training loop. So since the data is pretty simple, I think we can limit. So first of all, let's define how many epochs it will run. Let's take it for 5. So for 5 epochs, it will be running over the entire data set, and it will be calculating loss and then updating it. Okay, so let's define the learning rate, the eta parameter, hyperparameter. I hope this is again a hyperparameter which need to be tuned, but yeah, slow learning rate might cause you to land in a, I mean, might skip you the global minima, and then a high learning rate might skip the global minima, and then a slow learning rate might cause you to land into a local minima. So that's a fine tuning what we can do over there, but yeah, that's pretty much it about this. Now we need the weights list, w1, w2, w3 to pass into the forward pass, and then we need the bias list b1, b2, b3. And then for this, let's write a list to which will keep a track of what's the losses we are suffering. Okay, cool. Let's see. For epoch in range and epochs. Now what we have, we can create a simple bar, like, to see how the progress is. So for that we have to import tqdm. From tqdm, import tqdm. Now we have our tqdm ready. tqdm basically provides a progress bar, so we can see like how our epochs and how the training is progressing. Yeah. So what we have to do with with let me check the syntax of TQDM first. TQDM is something with TQDM. Okay, total is equal to length of now what we have to do, how will it will work. Length of train data. I think it should work for us. And let's call it something data bar. This is the syntax for TQDM. So what it will do, it will create a progress bar, and then for each of the epochs it will iterate the process for this particular times. I mean how many training data we are having for each of the sample, it will keep on iterating over here. So this is how the data bar is done. Now we have to extract our input for I comma, what else we need our input, and then we need our label for I comma input and label, and then we need to enumerate will give us indexes, and then what we can do is our label is into actual hot, and our this particular input is in train data. In enumerate, then we have to zip it out, zip train data comma actual hot. Now for an instance we can do this print input dot shape, print label dot shape, and then just break it up. Yeah, so it ran for 5, so our input is of shape 784, 1, and then our label is of shape 10, 1. So yeah, we are working fine with this. Now what we have to do, we have to do our forward pass. So for forward pass, what do we need? We need the x, we need weights, and then we need bias. Weights and bias are the list, and then x is basically and then whatever we will be getting z1, a1, z2, a2, z3. So let's do the forward pass. z1, a1, z2, a2, and then z3 is equal to forward pass. X will be your input, and then weights matrix is whatever we are having. Okay, but yeah, I think weights matrices should be initialized. We'll update the weights here. Weight and then bias. We'll be updating this. Let's see if forward pass is working fine. Yes, it's working. We're not getting any error. Are there any print statement in forward pass? Oops. Cool. Not this. So our forward pass is working. We are having z1, a1, z2, a2, z3, and then our back propagation will be needing activation z. Okay, so dw1, dw2, dw3 will be backprop. Backprop will be an activation. Activation will be having a1 comma a2, and then we'll be having z. Z will be z1 comma z2 comma z3, and then actual will be your basically label, and then weights will be your weights matrices. I mean weights, and then input valve will be your input. Cool. Let's see if it's working fine or it's breaking anything. Okay, we got something. Then we're going to got tensor but expected one of tensor input, tensor other, tensor output. We are getting it with loss with C3. We are getting this error over back propagation loss with C3 softmax. Oh, why is it giving me XP divided by denom? exp should be a tensor, right? And denom should be tensor. What is exp and denom? Let me check. Shouldn't be happening. Yep, it is correct actually. Your exp is a tensor, your denominator is a tensor. What if I do this? Let's remove this. Exp yeah, fine. Something was messing up with this. Yeah, should be fine. Okay. Just remove this one. Okay, cool. So we are good to go with the backpropagation also. Now what we have to do, we have to do the gradient descent. So what we'll do is W1 will be getting updated with W1 minus learning rate into dW1, and similarly the other three weights also. W1, W2 will be getting with this, and then W3 will be getting updated with the derivatives of W3. Similarly, okay, dW3 is not here. Similarly, what we can do for the same thing for the bias, but we are not using bias much now. Now we can just update the weights to be W1, W2, and then W3. So now we are giving it the updated weights, and this is how I think we are done with one iteration, so we can do this thing, dot update one. Now what we have to do is we have to define a loss function over here. Like we have to check out how the losses are appending, I mean how the losses are working, and then we have to see that if the loss is getting decreased at every instant or not. So let's define a loss function over here. Let's define over here def cross entropy. For calculation of the cross entropy, the two things which we needed were the true labels and the predicted labels, whatever we are giving. So true labels, which will be torch dot tensor, and then predicted labels, which will again be torch dot tensor, and it will return again this way. So like cross entropy, it is basically what negation of some basically it is this thing, negation of summation yi log of si. So you can simply calculate equal to softmax of predicted labels. Predicted labels is basically z that is coming out, like it's not a good term to use, but yeah, predicted labels, and it will calculate the softmax along the dimension is equal to 0. And then what we can do is we can simply return minus 1.0 into torch dot sum, summation of what, multiplication of torch dot, well, not mat mul, it is just simple multiplication. So with star also it should work fine, but yeah, it's just simple multiplication. True labels with torch dot log predicted labels, not predicted labels actually, probab. Yeah, so that's our cross entropy loss. And then what we can do, for every 1000 of this particular iterations, we can simply check our loss, if the loss is increasing or decreasing, what is happening over here. So what we can do is just it's done. So if I modulus 1000 is equal to 0, loss iter is equal to we won't be needing this. I mean, okay, let's see. Loss iter is equal to cross entropy. True labels is label, and then our prediction is coming out to be in Z3. Break. Okay, so at this it will break. Let's see how it is going. Yeah, so it's working fine. Now what we can do is data bar dot set postfix loss is equal to loss iteration, and then just cut it out, paste it out. Yep, I think that's pretty much it. Let me see if I'm missing something. Yeah, I need to append the loss also. So losses dot append loss iter. Cool. That's our backpropagation. We are getting the derivatives, we are updating the weights, and then we are again doing the forward pass. So that keeps on happening until the number of epochs get completed. And this is pretty much it, I guess. And if we should, like, if the code is correct, we should see the loss falling down in a similar, I mean, in a regular fashion, unless it comes down to a stable point. Let's see how it works. We are running for 5 epochs, right? So currently the loss is at 2, now it went to 1. Now this is the first epoch. Let's wait for the time it happens. Okay. Yeah, so we are done with our training, and now let's see how the model is performing. So what we'll do, we'll load the test data, p.read csv, and then we'll do the similar thing what we did with the train data. I mean, just copy and paste. Control C, Control V. Yeah. Control C, Control V. And instead of train data, this time we'll be using test data. And then instead of actual, let's write actual test. Cool. Yeah. So now we have our test data and we have our actual test data. So now what we can do, we can predict using our model. Prediction is equal to, let's write this. Let's do this, and then for inputs in test data, let's see if it's correct shape or not. Print input dot shape, and then just check it out. Yep. So what we can do, we won't be needing anything. We'll be needing just the final value of the forward pass, what it is coming out from Z3, right? Z3 is the linear projection layer, so we want to be using Z1, A1, Z2, A2. So 4 underscores, and the last one will be needing. So 4 underscore and the last one label will be your forward pass. Forward pass will be X. X is your input. Weights. Weights will be whatever weights we have created over there. I think it should have gotten updated. Otherwise, this epochs wouldn't have been work. Yeah. So weights would be W1, W2, W3, W1, W2, W. 3, and then bias will be B1, B2, B3. And then what we can do, uh, is uh, predicted label is equal to torch dot argmax of, let's see if it's working or not. Okay, print. Yep, it is working fine. So what we can do is now prediction dot append predicted label. Okay. So now we are ready with our predictions, and one thing we didn't need to do any one-hot encoding for this actual test. I mean, there was no need to do this. I mean, it could be simply dot to numpy, and then we don't need all this because we are not calculating loss or any sort of things. So I think this should be fine. Now for I comma j in predict. Now let's calculate the accuracy whatever we are having in zip prediction comma actual test. If I is exact is equal to j, we are getting a correct count. Cool. Now we can do this print accuracy is count divided by length of test data. Okay, so I think something is getting wrong over here. Yeah, so I got my mistake and it was pretty silly. I don't know how the code worked, but what actually I did that, yeah, uh, instead of inputs, I was giving it input. I mean, we are having inputs over here. So I don't know where this variable is getting from. Maybe from somewhere up above in the back propagation or in the training loop. But it was reading this particular variable as, maybe it was getting this variable from here. Yeah, that's one shitty thing about Python. I don't know how, when, and where they will improve their scopes things. So it will be inputs because we are using for test data, and I was giving it their input. So now if I run it for the same code, and it took me like 20 minutes to debug because I was not able to figure out where I was getting it wrong. And then what we can do now, we can print the accuracy, and yeah, your accuracy is around 94.3%, which is pretty good, considering that I reran it for like 2 epochs. I'm sorry, for 3 epochs. So from 5 I reran it to 3 epochs just to see where I'm getting the error. But yeah, so now this is pretty much it. Now uh, yeah, so that's how backpropagation works, and that's how we code this thing. So yeah, this completes the video about forward propagation and the backward propagation. And the next video will be probably around a paper which is going on about the AI scientist. So we'll be discussing that particular paper, and then some related paper along with that, like it's a probability again. And yeah, we'll probably start working with LSTMs also. So we'll be following the same process and the same approach: LSTMs first theory, and then we'll be covering in the scratch. But yeah, most probably LSTM will be using the internal libraries, because coding it from scratch will be like a lot more than the backpropagation derivatives. I mean, we don't have derivatives over there, but backpropagation, it's like it will be very difficult for LSTM. So we can go with the forward propagation, but yeah. So that's pretty much it. I hope you enjoyed the video. So yeah, see you again in some other contents. Thanks.